In this video, I'll talk through the 2025 Higher Physics paper and explain how I would attempt each question. Starting off with the multiple choice. This question is asking us about a car accelerating uniformly from rest and traveling a certain distance in a certain time, and asking us for the final speed. If we look at what information we've been given, we have been told the distance, the initial speed, and the time. Of all the relationships in the relationship sheet, the one that does not have acceleration, that does have the things we know, would be half of u plus v over t. I'm going to do some shifting around so I can get v by itself. I'm going to times both sides by 2, and I'm going to divide both sides by t. And then I'm going to bring over the u and make it minus u, like so. Plug in the numbers, 2 times 18 on the top, over 3, minus 0, because we're at rest. And then that's going to give you 36 over 3, which will give you an answer of 12 meters per second. And that should match up to answer C. For question 2, when I first seen this question, I thought, this is great. I get to show off the fact that I know that in a velocity time graph, as the graph crosses the x-axis, it's going to change direction. And then I clocked, actually, this is acceleration time for that. The ball is moving vertically up and down. We are going to have gravity pulling it towards the ground. That means it's going to have constant acceleration. It's been dragged down towards the ground. It's going to be negative 9.8. We are looking for a graph that shows constant acceleration. If we look at A, we do have constant acceleration. So when we look at B, there is not constant acceleration. In C, still not constant. In D, not constant. And E, it's not constant, it is changing. The only one that has constant acceleration that I can see is A, and it is also negative acceleration. On to question number 3. We have got two forces opposing each other. I want to find the unbalanced force first. Straightforwardly, just take away the two values. We get 4 newtons. We are then asked for acceleration, so F equals ma. Rearrange for A is F over m. That means our unbalanced force of 4 on top, 2 is the mass on the bottom, and that gives us 2 meters per second squared, which is answer A in this question. So I find that one pretty straightforward. Next one, we have got an object on a block. Let's put in the information that we've got. Well, we're told the mass and the acceleration. We're told the force of friction acting on the block, which will oppose the movement. So it's going to be going up the slope like so. And we're told that is 6.4. Well, the fact that we have an acceleration means there is an unbalanced force down the way, which has to be bigger than the frictional force. If we work that out using MA, that will be 3.5 times 2.3, which will give us an answer of 8.05. The block also has to overcome the 6.4 newtons of friction, so add them together to get the total force going down the slope, which will give you 14.45 going down the slope. And then for the angle, we are going to be using either the sine or the cosine, the mg thing. It's parallel to the slope, meaning it's going to be the sine one. We can rearrange this for working out the angle. So first thing I'm going to do is take across the mg and get it on the other side. And then to get rid of the sine, we're going to do sine to the minus 1 of that. And then when you plug that in a calculator, we're going to get our answer of 24.9 degrees. Round to 25, answer of D for number 4. In question 5, we're asked about an object at rest at a height, and then the maximum speed. So this is feeling like potential energy converting into kinetic energy. So if we do EP, that's going to be mgh, so 9.8 times 0.2 times 1.6, which gives us an answer of 3.136 joules. At the point just before it hits the ground, the maximum speed would be all of that potential energy is converted in kinetic energy. So EP would equal EK, and EK is a half mv squared. So I'm rearranging, so times both sides by 2, take over the m and divide by it. And then we want the square root of that. Plug in our numbers, it will be 2 times 3.136 over the 0.2 that we had before. Take the square root, take the answer to that, and that will give you 5.6 meters per second. In this next question, we're asked about the mean force. This is an impulse question. And with impulse, we have to give each of the speeds a designation, whether we're talking about going upwards or downwards. So I'm going to make our downwards speed the negative one, hence towards ground, and then up the way it will be positive for the 3.96. And the relationship is FT is MV minus MU. As far as I can remember, it doesn't matter which way round you put the negative and positives. I've just done it because it makes more sense to me going down the way negative and positive going up the way. So we want the force. So the force is going to equal the right-hand side over 2. Divide both by T. Now start putting the numbers in. So the mass in both cases is 0.164. And then the final speed is the 3.96. And then you've got your minus 4.85 on the other side. And then all over 0.18. That's what this time says. Ping that in. I get out 8.03, rounded nicely to, or is exactly the same as answer E for number 6. Question 7 now. We're talking about dropping clay onto the ground. And X is softer than Y. Statement says that X comes to rest in less time than sample Y. Well, if it's softer, it'll be more bouncy. It'll take a longer time to stop moving. The mean force is less than the mean force exerted by the ground. Whether it's elastic or inelastic collisions, the change in momentum will be the same. It's the change in kinetic energy that's different. So in an elastic one, there is no change in kinetic energy, whereas in inelastic there is. But that doesn't matter for this question. It takes a longer time for it to settle, meaning that the same momentum change but over a longer period of time means it would be less of an average force. Whereas in number 3, it is the same change in momentum for both of them because they are the same mass. So that would, when we put it into the calculation, would be the same value that we've got for that, which makes it to me like number 2 is the only one correct. So B would be what I would say for that one. In the next one, we're talking about length contraction using in the relationship sheet. Our contracted length is the proper length divided by 1 over the speed that the thing is moving at over the speed of light squared, which as we start to put them in, well, we know the speed V is 0.999 c. We have our length at rest, which is the proper length, is the 26.7. And we are asked to work out the length as the proton is moving, which would be contracted. Plugging them in, then we've got V is 0.999 c over c. They will cancel out, the c's will cancel out, leaving us with 1 minus 0.999 squared. And then when we plug that into a calculator, that gives us 1.19 kilometers, which matches answer B. I just clocked that I had actually, when I wrote it down, I only wrote 2 nines instead of 3 nines. That actually wouldn't have given us this answer. It gave us like 3 point something. Luckily, it wasn't an option. So I just went back, put it in properly, and yeah, that's how you get it. So just watch out, you're actually plugging in the numbers correctly. Now on to number 9. We're asked about cosmic microwave background radiation, CMBR. Does that provide evidence for the Big Bang Theory? Yes, it does. As the light and everything was scattered through, it's moving there. It's coming from space. It will reach the Earth in all directions. They're saying the temperature was lower in the past. No, that would be incorrect. They are getting cooler. And then less energy means a longer wavelength of light heading towards the red. So that redshift idea for those ones, which means only the first 2 are correct. And that gives answer C for that one. For number 10, we are told the potential difference, and we're asked about the speed of an electron. We can, first of all, work out the work done, WQV, so that we then need the charge of an electron, which we can get on a data sheet. And then for our voltage, we need to clock that it's kilovolts, so it has to be times 10 to the power of 3. Or 1,200. Ping that in, gives us 1.92 times 10 to the minus 6 joules. Careful here, that is an option, the value is, but that is meters per second, what we're asked for. So they're trying to trick us, I believe. That gets converted to EK. We're going to use EK equals a half mv squared. Again, rearrange it for V. So the square root of 2EK over M. Plug in the numbers. The EK we get from the previous part, and then M is the mass of an electron from the data sheet. 9.11 times 10 to the minus 31. Pop that in, plug it in the calculator, and then that will round to 2.1 times 10 to the 7, answer of C. In this question, we're asked to determine the direction of the force exerted by the magnetic field on a proton. Now, I know there are different ways of doing that, so I have tried with the left and right hand rules, and that confused the life out of me. I came across the left hand slap rule, which makes a lot more sense to me. There may well be a reason why it doesn't work in certain situations, but this seems to have worked for every question I've came across on in these higher papers as we're making our way through them. So what it says to do is to take your left hand, and again, the camera might be flipped, so it might look a bit awkward, but that's my left hand. We take the fingers of left hand, and they're acting as your field, or pointing on your field. You've then got your thumb, shows the direction of flow. So in this case, they are a proton moving down the way. And then if it's negative, you would look at the palm, and wherever your palm is pointing is your force. If it's for a positive one, you use your knuckles. So whichever direction they're pointing in. With the fingers into the screen, so pointing towards the screen. The thumb is pointing down the way because the proton's moving from top to bottom on the screen. And then my knuckles are pointing, it's on the left in here. It's pointing to my right. As I'm looking at it, it points to the right hand side. Now there's every chance this gets cut out because this is confusing. I'm going to take into account the flip of the camera. So if here, my fingers are pointing into the screen, my thumb is pointing down the way, and then my knuckles are pointing to the right as the screen is showing it for that. Try it and see if it works out. If you prefer to use your finger forky things, go for it. If you prefer to do the other rules, that's fine. There's probably a reason, but like I say, if you follow these directions and you're looking at your own hand, you should get that it also goes to the right for E as the correct answer. Question 12 feels like home. This is very chemistry oriented. We have got to look at the differences in the top number, the mass number, which is 4. Bottom number is 2. 4, 2, He is an alpha particle. If it was beta, it'd be 0 minus 1 E, because it's an electron. Neutron, 0, 1 N. Proton, 1, 1 P. Answer A for this one. In this question, we are told distances and we are told irradiance. The one that would make most sense to use here would be I1 D1 squared equals I2 D2 squared. We have got our first distance of 0.4. We're told our first irradiance and our second irradiance, and we are asked to work out the distance. I'm going to rearrange to work out our I2. It's just moving the D2 over to the other side. And then we want to take the square root of the I1 D1 squared over I2. Plugging that into your calculator gives us an answer of 0.2 meters, which gives us our answer of C. So just make sure you know which ones are together. Make sure you were talking about the ones at the beginning, the ones at the end, in the right places, and that should hopefully line up nicely for you. As I was going through this, I remembered the inverse square law, that as the distance doubles the intensity, the irradiance quarters. If we look at what's happening, well, our irradiance is quadrupling times it by 4. If doubling distance quarters I, then halving the distance would quadruple the irradiance, which is what's happening here. So half the distance, half of that would give you 0.2 as well, which is probably a quicker, more straightforward way of getting to the answer. In this question, we're talking about photo emission. So by the absorption of radiation with enough energy to cause electrons to move. Okay, so we're going to be thinking about energy in the first couple. So it is asking us about replacing UV with visible. Well, visible light has a longer wavelength, lower energy. It would not cause more emission to happen. So that's going to be incorrect. Infrared has also got a longer wavelength. So for both those reasons, they are incorrect. If we shine less light onto the surface, well, there's going to be less potential for the photo emission to happen. So even if it had the right frequency and had enough energy, we're sending less light towards it. That's not going to work. The connections, well, this is, I think it's right, long one is positive and then negative connections, which means something. We'll come back to that one. Allowing air, well, air can absorb UV radiation, so that means there'd be less radiation striking the surface, meaning there's less potential emission happening. So by that process, that would let me get to D. This must be something then about the electrons moving in a certain direction. So the electrons would flow now towards the zinc plate. Not sure exactly, but by my process of elimination, I managed to get it down to D as the answer. Maybe not the most satisfying way of getting it, but number 15 takes me back again to chemistry. We have got a wavelength and we've got an energy. I don't think we care about that energy. We're asked about the energy of each photon. This time I'm going to use E equals hc over lambda. That is a combination of two relationships. That's E equals hf and f equals c over lambda. So if we sub in c over lambda for f, we get E equals hc lambda. You can do it in two parts. This way I can just put it in and it will spit out my answer. Planck's constant is 6.63 times 10 to the minus 34. That'll be in here somewhere, I'm sure. There we go, 6.63 times 10 to the minus 34. It's the speed of light, 3 times 10 to the power of 8. And then our wavelength needs to be in meters. So times 10 to the minus 9 after the 250. Plugging that all in, spits out an answer of 7.96 times 10 to the minus 19 joules, matching to D, rounding to 8 times 10 to the minus 19. Moving now on to question 16, we're asked here about an interference pattern and we're told about its minimums that we are dealing with. So the first thing I would do is mark on my first and second minimums. That'd be X and then Y. We can then go to the relationship sheet. And for this type of question, we have two options. We have the M lambda or M plus a half lambda. We are talking about a minimum. And that's going to then be when they're half out of phase. So it should be the M plus a half one, like so. And we want to use that. So if we are able to, what do we know? We know the path difference. We know that it's the first minimum. And then we can work out the wavelength. I think that's what we need to do first. So let's do that first. So rearranging it. We will get the path distance over M plus a half. Path difference is 300 take away 50, which is 50 millimeters. Would we want to put that in meters? Well, your answers are in millimeters. I'm going to leave it there. It's the first minimum we're dealing with just now, which is when M is 0. And then the second would be 1. Third would be M equal to 2. So 50 over 0 plus half, which is just a half. And then 50 over a half gives you 100 millimeters for the first one. We are then dealing with the second minimum, which would be, or two ways of doing this. The way to use the relationship, what we could just plug that in. So path difference for the second minimum is going to be 1.5 times the wavelength, which is 100, which would give you 150 as our answer. And I'm kind of spotting here where if we know that it is 100, the wavelength, and the difference is 50, just add on 50 to 100, gets you 150 as well. So I've probably went a long way to get it, but still got the right answer. Hopefully, in the next question, we're asked to deal with information about the critical angle. And in the relationship sheet, it says that sine theta of the critical angle is 1 over n, which is the refractive index. So let's ping that together. How is that going to help us? Well, we could work out what the refractive index is by doing 1 over sine of the critical angle. And then that gives out 1.66 and a few other numbers after that. The other relationship that will help us is how we can work out the refractive index. So n is the refractive index, and that's sine of the two angles. Could be two wavelengths or could be the two speeds. We have got, well, some of the angles. Something we would need the incidence, angle of incidence, and angle of refraction. So when dealing with n equals sine theta 1 over sine theta 2, the top one is going to be when it's in air, which is after it's been refracted, so outside at the bottom. And then the other one would be in the glass, in this case, the setup we've got here. So the angle in the air, well, we need to be careful that we're dealing with the incidences between the normal and the light coming in, and refraction is when it's coming out. So it would need to be 90 take away 40, which would be 50, not putting 40 in. So our angle in the air is 50, and we are trying to work out the angle in the glass. So rearranging it however you usually do it, that would bring me to get 27.45 degrees in our block angle. So if you miss the refraction part, that would mess up your answer you're going to get. Next up, we're asked about frequency, speed, and wavelength. Two things I remember is that frequency doesn't change, but it will slow down within the block if the block has a higher refractive index. So putting them together, well, if the frequency needs to stay the same and speed equals frequency times wavelength, well then frequency equals speed over wavelength. To keep the frequency the same, well, if the speed goes down, so we have a lower number on top, well, the wavelength would also have to go down to keep the frequency the same. So both the speed and the wavelength in this situation have to go down. We start off with just C as the speed, so we have to have less than that. So C, D, or E have half of that. Wavelength would need to be a half as well. And then the frequency would have to stay the same. So whatever happens to the speed, so if the speed decreases, the wavelength has to decrease. Speed increases, the wavelength has to increase. So yeah, frequency staying the same is what helped me. In this question, we're asked for the total resistance between X and Y. We need to spot that there are two sections to it. We have a parallel section and we have just the other resistor in series. That means we have to treat them slightly differently. So for part B, the bit in parallel is 1 over RT equals 1 over R1 plus 1 over R2. That means that 1 over RT will be 1 over 8 plus 1 over 2. Popping them together and rearranging 1 over 0.625. That would then give me 1.6. When we then take into account, they've also got a 4 ohms resistor to include as well. We add that on, and then the total resistance would be 5.6, and hopefully answer D. In number 20, we're asked about the greatest power dissipated. We are told in the diagrams the voltages and resistances. If we look at our relationships, we have got that P equals V squared over R. Makes the most sense to use that one with what we're told. If P equals V squared over R, we want two things. We want to have the highest voltage that we can, and we also want to have the lowest resistance that we can. First, starting with the voltage, we're thinking about parallel versus series. In parallel, all the branches will have the same voltage, the same as the supply, whereas if there's any series, it will split. So what have we got? In the first one, it is all in parallel, so it will have 6 volts across it. The next one is in series, so it'll have less than 6 volts. In this one, again, it's in series, so that will have less than 6 volts. In this one, the lamp is in series with the 3 ohms resistor, but it's in, nope. The lamp is in parallel with the 3 ohms resistor, but there's also in series, those two are in series with the 6 ohms resistor, meaning that it would have less than 6 volts, and the bottom one is in the same boat, meaning that the only one that you can get the maximum number on top would be A, because you have your 36 volts on top. If you had two that were kind of similar, you might have to take into effect the resistance. We'd want the lower resistance component, because then that'd increase the power, because the resistance is bringing down the value as it goes through. But I managed to get that just from the NAT 5A rules. In this next question, we have been given a circuit and we're asked about the EMF and the resistance on the, and the reading on the voltmeter across the top. Okay, so what have we got? Well, we know the resistance and we know the current. So we've got both of them. So with EMF, I think we're wanting to use the E equals V plus IR, which is when you've got your EMF, which is the maximum, you've got your TPD, the terminal potential difference, and then this is your lost volts, so internal resistance times the current. For that, we are asked to do two things. So one of the things I would probably want to do first is work out the lost volts due to the internal resistance, which would be the current, which is 0.15, times the internal resistance, which is 3. That will give us 0.45 volts has been lost. So what that means to me then is that, well, the EMF, take away the voltage, would have to equal 0.45. That is not the case in A. There's not a difference of 0.45. Second one, nope. Third one, no. E doesn't have that. That means D would be the answer I'd pick for that one. In this next one, we have, again, a setup with the EMF and the internal resistance. And one thing that might come in handy is that both of the resistors are in parallel. So we might need to take that into account. So we know the EMF. So that's leading me again towards the EMF equals the TPD plus the lost volts. Can we work out what can work out? Well, we are told the supply voltage and the resistance. And then the TPD would be the current times the resistance of the circuit. How does that help us then? Well, can we then sub that in? So the EMF is going to equal IR plus the lost volts, so I times internal resistance. And we know them. Oh, we're trying to work out R. That's how it's going to help. Then rearrange it for R. Well, R is going to be the EMF, take away the lost volts, divided by the current. The EMF is 12, so 12 take away 0.4 times 4, all over 4 is what we get there. And then the resistance is 2.6 ohms. Now, oh look, that's answer B. And someone might have just went, oh great, I'm going to take that answer. However, we are ignoring the fact that they are in parallel. That is RT. And 1 over RT is equal to 1 over R1 plus 1 over R2. And when we then plug in our numbers, that means 1 over 2.6 is going to be 2 over whatever the resistance is, because these resistors are identical, as it says in the question. Bit of rearranging means that R is going to equal 2 times the resistance that we worked out. So 5.2 as our resistance for each resistor. And then that will give you an answer of E, hopefully, for that one. In this next one, we're asked about valence bands and band gaps and things like that as well. For me, chemistry's helping here because it's saying that the gap is bigger for LEDs that are red. Well, the larger the gap, the more energy required, which means you need a smaller wavelength. But red is a longer wavelength than blue, which means it's got a lower energy. So that can't be right. LEDs emit photons of longer wavelength. Well, I just said that, so that's true. Potential difference determines the wavelength. No, it doesn't. It's the gap, the band gap between the valence and the conduction bands, which has nothing to do with the potential difference. So that should just be the one. Number 2B should be the correct answer for that one. Number 24, we are asked to work out the mean value, which is when we'd add them all up and divide by the number of numbers. When we do that, we get an answer of 0.3 meters per second, which gives us which narrows it down to C or D. When it then comes to the random uncertainty, if someone forgot how to get the random uncertainty, it's in the relationship sheet, which is max value, minimum, max, takeaway min over number. So in this one then, so plugging that in, our maximum value 0.34, minimum value 0.28, all over 2, 0.06 over 2 gives 0.03. That's not an option, but if we were to round it, then that would give you what's closer to 0.01, isn't it, than 0.06. So round it down to that. A would give me C as my correct answer. And that, yeah, hopefully right for that. So yeah, data, the relationship sheet came in handy for people who have not remembered what calculation to do for random uncertainty. Next one, we are given a calculation to do. Just need to follow it through. We are asked for R. We have to work out R, the radius. So let's start plugging them in. What's going to be 2 times the universal constant of gravitation. That's in the data sheet. So we have to include 6.67 times 10 to the minus 11. And it's 2 of them. Then M is the mass. So that's the 1.99 times 10 to the 31. And then speed of light is just going to be 3 times 10 to the power of 8, which we need to square. And then calculator takes care of it. 29496. Round that. 295 to C. 2.95 times 10 to the power of 4 meters. Moving on to section 2, we are asked here about a spider cam, which helps film sporting events. We've got cables, and you can move the height and the position and things like that around. First up, the aspect acceleration. That is the change in speed over time. And then because they've given us a value, we have to say that exact change that's happening. So it's an increase in velocity of 1.45 meters per second every second. Next up, we are asked to work out the distance travelled from rest to maximum velocity for that. Okay, so we've got maximum velocity, we've got rest, we've got acceleration, and we're asked for a distance. So this time, we want acceleration. And we want to work out a distance. So no, that's nothing to do with acceleration. So no time. We aren't told the time where we know, so that's no good to us. Get rid of the timey ones. That's get time. That leaves me with just the one. So final speed squared, initial speed, and then 2 acceleration, and then that'll be our distance for S. Then let's give it a go. So V squared equals U squared plus 2S. Bit of rearranging. So I want this by itself. So if we move that across and take away, so V squared take away U squared, it's going to be the 2AS, and then S will equal that thing all over 2A. So then numbers, get this right. So maximum final speed is or final velocity is 8.86 squared. Take away what's from rest, so that would just be 0 squared, which doesn't change anything, all over 2 times 1.45. And that will hopefully spit out a lovely answer, which will give 27.1 meters. Like that. That should be that one. Okay, and this one we're talking about the tension, which is caused by the weight of the object pulling down and holding it in there. So that may be a good shout, first of all. So W equals mg, W equals mass is 31 times 9.8, 3.8 newtons. There are 4 wires, so each wire would be responsible for holding up 1/4 of that. Then this is where we have to work out which thing, cos or sine. And because we're dealing with the weight, which is the vertical section, well, if it was going across the way, it'd be cos, so it's going to be sine. So we're talking about f sine of the angle that we're dealing with. And we've worked out that each of them is responsible for 75.95. Right, let's see if I can remember my triangle stuff. So we've got a right angle there. That's our weight. And they're telling us that T is going this way. And we're given that angle in there, aren't we? Yes. So that's going to be then your opposite. That's going to be your hypotenuse. So saw, ka, so saw. Sine. Yes, it is sine. So that means that the sine of theta is opposite over hypotenuse. So sine is going to be our weight, which is 20. Nope. So the sine over 12 is going to equal 3. The tension in one of them, all over our tension. Rearranging it then, T, our tension, is going to be 75.95 over sine of 12. And T comes out as 365 newtons. So if you're ever unsure of which way around it is, the triangle seemed to have helped me there. So set up your triangle, look at your angle, designate them opposite, adjacent, and hypotenuse, and then look at which one you're asked about. So you're asked about this one, so we have to have a calculation involving the hypotenuse, and we also know now the weight, so we know the up and down bit, we know the opposite for that. You could probably have done it without, you could probably have divided by 4 at the end, as long as at some point. So what I mean by that is, say you kept the 303.8 still over sine 12. Well, that would give 1461 newtons total. And again, remember that there's 4 of them, divide that by 4 does give us 365. Wee bit different after the decimal place, but it would round to be the same thing as well, just depending on what one makes more sense to you. In this next one, we're going to be talking about law of conservation of linear momentum. That is that before and after, the momentum will be the same. So the total momentum before collision is equal to total momentum after collision in the absence of external forces. We are going to use the mv minus mv mv minus mu again. This time though, because at the beginning and end are going to be the same, we're going to be using like m1 and m2, so before and after it. And we'll get p and q. So, and in this one I'm going to make going to the right is positive and going to the left negative. And vehicle P is going to the left, so I'll make that one negative and the other one have to be positive. Okay, so moving at, so that's initial, so that is U, P, and then this one in here will be U, Q, and then this will be afterwards, so V, P. So we're going to do some moving around to try and get to the final speed of Q at the end, all by itself. So this will move over and take away. And then we're going to be dividing by MQ. My before section stays the same. We're going to take away the P part afterwards. So MP, VP. And then all over MQ. And now I need to watch out for my positives and negatives. So MP is just going to be the value, so 0.18. Times by UP, which I've said is 100 and, which is 1.2, but I'm keeping that positive. And then MQ, 0.24, times by negative 0.64, and then take away MP is still 0.18. times by VP, which is going to the left, so that's now negative 0.76. And then that's all over the mass of Q, which was the 0.24. And very carefully enter this into your calculator, which spits out for me 0.83, and velocity will be meters per second for that. So make your decision if you're going to go right positive or left positive. It doesn't matter. Doesn't matter. As long as you consistently apply that throughout the thing. Putting in the letters helps me to make sure I'm not messing anything up. And then watch out how you're rearranging it. And then also make sure you're putting them in, typing them in correctly. And hopefully that will go smoothly. Show by calculation whether it's elastic or inelastic. Here we're going to be looking at EK. So momentum's conserved. But it depends on what happens with the EK. So if EK stays the same, so conserved, that means we've got an elastic. Versus if it's not conserved, that's going to be inelastic. Let's set it up for before. So EK equals, so we need to take both of them together. So I'm just going to add them both together. So it's half of the first mass was 0.18. And the initial speed, so this section in here, 1.2. That would need to be squared. Add on a half of the other one. So with this section here, 0.24. That is, where are we? 0.24 and 0.64. That needs to be squared. And I get that to be 0.179 joules. And then now we need to repeat that for the after. Our masses will stay the same, but it will be the velocities that will be different. So 0.76 and 0.83 we worked out. And for me, that comes out as, I get that as 0.135 joules. Not the same. And that makes it an inelastic collision. Total energy before is different from the after energy, therefore it must be an inelastic collision. Next part, we have got an air track set up to show the Doppler effect. We're given two values of frequency. We've got the frequency at source. We have the frequency at source and we have the frequency that's measured, the observed one. We're asked to calculate the speed along the track. And in this question, we want to use this one. And when we are deciding whether or not to use a positive or negative, if it's moving away, we're going to add it on. And if it's coming towards, you're going to take away. So negative when it's coming towards us. It is moving towards the microphone. So we're going to use the negative version here. I'm going to start to rearrange this a bit to try and get the VS by itself. So the V minus Vs, I'm not really liking on the bottom, moving that across and multiplying by it. And then I can start plugging in some of the numbers that we've got, making sure we're putting the Fs and the Fo in the right places. Some more rearranging, taking the 849 over to the other side, divide by it. And then I am wanting to swap them around so that I can get Vs as a positive value. So I'm taking the Vs, moving it to the opposite side. I'm taking that whole fraction and moving it to the other side and taking it away. Personally, I prefer to rearrange everything before putting the numbers in. I was trying that with this, and this is just not the type of relationship to do that with. I was getting myself muddled up and confused. So starting to put numbers in, we can start to simplify it down. And then when we get our answer, it's going to be 1.6 meters per second as our answer. For the next part, we're asked about wavefronts and why the frequency would be greater, by why the frequency emitted by the microphone is greater than that emitted by the buzzer. We have to remember that it's moving towards the microphone, which means that there will be more waves reaching that point. Every release of an wavefront is going to happen from a closer position to the microphone. And then more wavefronts reaching the microphone every second means that it's a more frequent, means it's got a higher frequency. And then that would get us an answer for that one. In this one, we have someone who isn't able to hear the change in frequency, and we are trying to describe a way in which we can make it more obvious. If you increase the speed of the vehicle, then that will cause a greater effect and cause a greater change in the frequency. You could also have the vehicle traveling straight towards the person, or if they're in between the tracks or something like that, that might make it more obvious, but a faster speed makes it have a bigger effect. In this next one, we're asked to use our knowledge of physics to comment on how this activity would work. So in this one, the member of staff is going to jump, and that's going to cause the visitor to go flying. Things to do with this would be things like potential energy and kinetic energy. Gravitational potential energy converted into kinetic energy, and then that will then act to throw the visitor forward. The relationships EP equals mgh and EK is a half mv squared would come into this situation. So the bigger the staff member, the more potential energy they would have, and then the more kinetic energy it would result in for the visitor. And then as well the height. If they jump up, then that's going to increase the height, and that's going to give them more potential energy, which would result in more kinetic energy. And then you get the large upwards force that throws the person through the air. Also could talk about the Newton's pairs and how the downwards force the downward force will have an opposite and equal upwards force on the visitor, and a bit of FMA. We can talk about impulse, where Ft equals mv minus mu, so the change in momentum and the time that takes. So because it's happening very quickly, the person's not waiting, lying ages to slowly be thrown through the air, it's acting pretty quickly, then that's going to then mean that there is a large momentum, upwards momentum, and that's going to launch them further. We could talk about having the pressure of the airbag. If the airbag was deflated, this wouldn't have as much of an effect. I'm now thinking, could have talked about the fact that if it was really, really inflated, then that could potentially be too much pressure and cause it to burst. But they'll have some sort of safe levels to do that in. They've also got a bouncy surface to land on, which will spread out their force, and that will make it less of a rough landing. So things like pressure is force divided by the area. You increase the landing area, you decrease the pressure, keeping the same force. With these kinds of questions and the similar ones in chemistry, you don't get very much guidance about what's acceptable or unacceptable answers. We get 3 marks for being good, 2 for being reasonable, 1 for being limited, 0 for having no understand or showing no understanding. I would hope that would be in the good category. There are most definitely things that I've not even thought of including, but as long as you have enough information to make it good, that picks up the full marks there. In this one, we're asked about the term for the change in the measurement of time for people moving at high speed compared to a stationary observer. That is time dilation. That's what we're doing with that one. We're asked then to work out the time interval measured by the observer on the nearby planet. We have speed, we have time. So in this one, t prime, t with the apostrophe, is equal to t over the square root of 1 minus the speed that the thing's going at, divided by the speed of light, and then that needs to be squared as well. We are given some information. Let's see what we're doing. So we are working out the one that would be measured by an observer. That's going to be our dilated time, our t prime. So yeah, we have to work out dilated time, and we're given what the proper time is for the person in the same frame as them. I think that's how you say it. We could then start plugging in the numbers. We've got our speed, 2.29 times 10 to the power of 8, and then 3 times 10 to the power of 8, because we're heading towards the speed of light. And then just fire that all into your calculator, and we get an answer of 379 seconds. So dilated means it's going to get bigger, so that makes sense. The dilated time will be longer. It appears longer for that one. Moving on to the next one, they're asking us about train drivers travelling at 80 meters per second for large distances, and they'll need to reset their watch's frequency. Well, the effect that we were just talking about only happens at speeds close to the speed of light, and that is not what's happening in this situation. Again, I'm not too sure on the word in there specifically, but they are nowhere near close enough to the speeds that make this effect happen. So that would be an incorrect statement. In question 5, part A, we're asked to compare values in terms of orders of magnitude. We want to do the big one divided by the small one. Make sure we're taking surface temperature for star 2 and star 1. So that's 210,000 over 2,290. That gives us 91.7 times bigger. And with these ones, we want to get it to our powers of 10. So 10 to the power 1, 2, 3, etc. It's closest to 100. 100 is 10 to the power of 2. That means that what was the hot one? Star 2 has a surface temperature 2 orders of magnitude greater than star 1. And that should pick up the marks there. Then in this one, we are asked to add a line to show how the energy emitted per second per unit area varies from star 2. So this is the sun and then star 2. If we check the difference, star 1 and sun and star 2 is a higher temperature. That means it's going to be higher energy, shorter wavelength. And that's two things we care about here. And then these ones, we're talking about the peak, so where the highest point on the curve is. And if that's the case, then we are going to want to shift towards the left-hand side, our peak. And we want to make sure that because it's higher energy and the y-axis is energy, it has to be taller. So it has to go up higher. So peak to the left and higher and something like that. And I'm not going to tell you how many times I tried to make this happen to make it actually look like a curve. But yeah, the peak is the kind of focus point, I would say, for that one. Why is star 1 more red than the sun? So star 1, I presume, is colder. Yes, so has a lower surface temperature, which means it would be a lower energy, longer peak wavelength of light than that one. Next one, we're asked to work out the gravitational force, and that means we are using the relationship the way it is. So this is one of I would call the more straightforward ones. So we're plugging in our numbers. We need to have so for G, we'll find that on the data sheet. Our universal constant of gravitation, so 6.67 times 10 to the minus 11, which I'll bring over and use there. The masses, it just tells you both the planets. Planet A, the 6.09, and then the other one, 1.77. And then the R is the separation distance. So that's how far away the centers of both of the objects are. And then here, they've given it as 1.81 times 10 to the minus 11. These are the ones where you might have to involve the radius, and it's the radii of both of them plus however far away they are. This one, again, seems quite... Well, I'm taking it as being quite straightforward. Plug in the numbers, use your calculator to deal with all those things. That comes out, and for me, that came out as 2.19 times 10 to 21 newtons. For the next question, we're asked about the changes in the gravitational force of attraction when we change different things about the planets. So the two facts that are going to help with this one are that if you double the mass, you double the force. And if you double the distance, you quarter the force. What are we doing then? We have got something that's 3 times the mass. So if doubling the mass doubles the force, then tripling the mass will triple the force. And we're now doubling the distance, which means we will quarter the force. That means it will be 3/4 of the original. And I've just written down those two parts. So yeah, triple mass, triple force, double distance, quarter force. So we need to make sure we're clear in our head which one's which, because you can go down different pathways and wrong pathways there. In this next one, we have a graph showing the brightness over time as a planet passes between the star and the observer. That means they're going to block out some of the light. We are asked about planet A. Now, planet A compared to B. So planet A is bigger and also has a shorter time to orbit. So that means you're going to have a larger dark zone, so lower brightness. But if you see here how long it's taken, like it's down at that lower brightness for that length of time, it would be a shorter time because it's going to be moving around it more quickly. So how do I set that up? Well, I'd want to start in the same brightness because that's just the brightness of the star, unimpeded. We want our dark spot to be shorter, so I'm going to make the bright lines longer. And if it blocks out more light, we have to have a deeper ditch, crevice, dip, trough, whatever you want to call it. It's going to need to go further down, and then that will come back up. I've not really put mine's curvy because of the way this software works. It was a bit of a pain, but that's the idea we should be getting, that it starts going down later in the time, and then it goes down even further, and then it goes back up. That should hopefully pick up the mark there. In this question here, we're asked about why energy is released during this decay. There must be some of the mass has been converted into energy. In this one, we're asked to work out what that energy released would be. So we need to look at the mass difference. Well, the americium atom is our original. That's the starting mass. It's just going to be that by itself. And then the products are the neptunium and the helium nucleus. So they're going to go together to give us our final mass. Calculate the difference by taking them away from each other. And we get a change of mass of 5.3 times 10 to the power of minus 30. We have got mass. We want to get energy. That means we're going to be using E equals mc squared. Plugging that in. Well, we know the mass is the speed of light. Plug those values in. Calculator takes care of the rest to get us an answer of 4.77 times 10 to the minus 13 joules. Next part is like something from National 5 Chemistry, where we want to emit a beta particle. That means that the atomic number, the bottom number, goes up by 1, and that will be, the mass stays the same, so it'll be 14.7 nitrogen, and nitrogen is the answer. Now, if you're not sure of which elements are which, you can use the periodic table, which is in the relationship sheet, and you'll see there, number 7 is nitrogen. So studies of this decay show that the mass energy equivalence is different. So it's more in the carbon, so the original chemical, than the products. So there must be something else that's being made as well. So that would be your extra particle has been released. And that would be the neutrino. Something else has been made. Possibly neutrino. And the next one, we're asked about quarks and fundamental particles. They cannot be broken down into any smaller particles. They are not made of any other smaller particles. Here we're asked about 3 quarks. This is either going to be the baryon or the meson. B big, and then M mini, smaller for that one. So that will be the baryons. Next one, we have to deal with various different charges on the different quarks that are joining together to make this pentaquark, which has got 5 things in it, and it's 4 quarks and 1 antiquark. So we're told information here. And so we've got 1 up, 1 down, 1 strange, 1 charmed, and 1 anti-charmed. We have to work out the strange. So the anti-charm has to be the opposite of the charmed. So instead of positive 2/3 E, it would be negative 2/3 E. I'm just going to write out the ones that are going together. So up, down, charmed, anti-charmed, and strange. That has to equal 0, because the question tells me that. Plug in our numbers. And I'm just putting in strange just as my placeholder, because we're going to work out what that is. We should see that, well, if you've got a charm and an anti-charm, they will cancel each other out. And then we've got 2/3 plus minus 1/3. So 2/3 take away 1/3 is 1/3. 1/3 E plus the strange is 0. So they have to have opposite charges. So this range would have to be negative 1/3 E to get our answer there. In this next question, we are asked to state what is meant by the term irradiance. Well, we are told in the table that the units are watts per meter squared. Watts is for power, meter squared is for area. So that must be then the power per unit area. Power per meter squared in this one. That's quite helpful for that. We're then asked to use all the data to establish a relationship between I and D. I'm just going to label these just to make it easier to follow them through. So we are told D, we are told I. If only there was a relationship sheet that had something that had both of them in there. So I equals K over D squared. Well, if I equals K over D squared and we have D and I, we can work out what K is. So K is going to be those two multiplied together. Remembering to square the distance. So take my time going through them. I'll put in A, B, C, and D's values like so. And then just typing in the calculator, we get our answers here. And they are all pretty much the same. They're very closely related. That means that all sets have the value of K as the same thing, 7.9 to round it. And then that should hopefully be what they're looking for there. We are asked for two improvements that aren't repeating and calculating on average. We've got our distances jumping by 0.2 meters every time. If we did more distances in between those, we can see more about the exact trend that's happening as you go through. Or you could use a more focused beam of light. So rather than the light being quite diffuse and spreading out, you could have one that's kind of targeted, and that might make it a better experiment. Now, in this question, we are asked to work out the power when we're given a distance, a diameter, and the irradiance. That's leaning me towards irradiance is the power divided by the area. So we have most of the things for that. And then that means power is going to be the power will be the irradiance times the area that we're involving. And we've got the irradiance, 1.51 times 10 to the 3. We don't have an area, but we are told the diameter. It's a uniform circle. So pi r squared. If the diameter is 1 times 10 to the minus 3, then the radius will be 5 times 10 to the minus 4, or 0.0005 meters. Plug that in. We need to square the radius. Gets us this lovely answer here. 7.85398 times 10 to the minus 7. Move that over into our relationship on the left. And again, calculator will deal with that for me and gives me an answer of 1.19 times 10 to the minus 3 watts as my answer. So in this one, our laser has moved distance, but it hasn't changed. Well, that would be that the laser beam isn't spreading out. So that is that targeted light source. So it's not going to spread out for that, I would presume, because it only affects the ones that are spreading out. Non-diffuse is probably a better word for that. Next one, we're talking about the photoelectric effect, where radiation with the correct wavelength, correct energy will cause electrons to emit from the surface. Why does that show evidence supporting a particle model of light? Well, each photon has a fixed quantity of energy, and then that's what then, if it has the correct energy, it will cause this effect to happen. Work function, so it's the minimum energy required for electrons to be emitted. Next up, we're asked to calculate the maximum kinetic energy emitted from the surface of the metal plate. So we need to look for the frequency of the light coming in, and then also looking at the threshold frequency that's required. So energy coming in is the 1.3 times 10 to the 15, and then Planck's constant H is in the data sheet, 6.63. Where have you gone? Oh, over this side. Times 6.63 times 10 to the minus 34 joules per second. Pop that in with the first bit. Now, this one took me a wee minute. I was looking and going, well, I don't know what the frequency is of the... I don't know the threshold frequency, which is to do with the minimum energy required. So I was going to turn that back into frequency. But then I realised, well, to do that, I would divide it by Planck's constant, because if E equals HF, then F equals E over H. But then to put it back, basically what I'm saying is that is it. It's there. The work function is the energy required for the minimum energy required. That is the threshold energy. So I can just plug that in, making my life easier, and then pop it through. Gives me 2.73 times 10 to minus 19 joules as my final answer. And next we're asked about moving the lamp away and asking if that will affect the maximum kinetic energy of the electron emitted. The energy emitted is to do with the frequency of the photons, not the distance, not the irradiance of it. So going back up to the fact it's the difference between the energy coming in and the threshold required. Well, we are not changing that. If we change the frequency and increase the frequency, then yeah, it would. But it's not going to do that. What this would do is there would be less electrons being emitted. So the rate of photo emission would change, but not the maximum kinetic energy. That one there. In this next one, we're talking about a green pigment chlorophyll from plants and in biology. We're asked about why our central maximum is white. Well, in this one, there is no path difference. All of the wavelengths of light will all combine at this point to show white light is what's happening there. Whereas as you do have path differences, that's when the colour seen is going to change as it's going through. We are then asked to calculate the angle between the central maximum and the violet end of the spectrum, and we're given a wavelength. To do that, this is the relationship we want, where, and D is to do with the slip separation. We've got the sign of the angle, and then we've got the order, and I think we're talking the first order, and then the wavelengths we're talking about. So let's start seeing what we can fill in. We are trying to get what the angle is. So I've rearranged everything to get that by itself. So divide both sides by D, and then do sine to the -1 of that fraction. Plug in the numbers. Well, M, it's the first order maximum, so that's going to be just a 1. So we can ignore it, basically. And then 412 times 10 to the -9 nanometers into meters. At this point here, we have to work out the split separation. Well, we are told up here that we have 1,000 lines in every millimeter. So to get that value, we need to take our distance it covers divided by the number of divisions, which would be 1 millimeter, or 1 times 10 to the -3 meters, 0.001 meters, divided by 1,000, because there were 1,000 slits in that distance. That gives us 1 times 10 to the -6, which if we then put into the calculation, that spits out 24.3 degrees as our angle. And the next one, we're asked about why light passing through the sample would be green. If you're doing higher biology this year or you've done it before, that is a kind of standard question about the plants, why certain plants need different pigments to absorb light. That is because the chlorophyll absorbs red and blue very well, but doesn't absorb very much green. That green light would be transmitted through the sample, and then you would see green on the at the end of it. So it absorbs, takes away the red and the green, the red and the blue parts, and leaves the green light, and the green light is transmitted. Now we are asked about using a different number of lines per millimeter, and they're saying that that will let us more accurately determine the wavelengths of light. So their idea would be to split them more, and you can see them more easily. So to work out the spacing of the lines, it's again the distance divided by divisions. So it's the same distance, but this time less divisions for that. So that would then mean we've got larger spacing, and then a larger spacing causes smaller angles. And if, like me, you're not too sure which one it is, plug them in. So do the calculation. Everything else would stay the same. So this time when you use, so here on the bottom, instead of 1 times 10 to the power of 6, use the 4 times 10 to the power of 6. And then that will spit out a smaller angle. And then because there's a smaller angle between them, it's more difficult to see which wavelengths were absorbed. because there'd be more kind of overlap between them, is what we'd want, something like that. Just realised I should just take the few seconds to actually put the numbers into the calculator. So here we're using the new divisions. We end up with an even smaller angle, making it more difficult to tell apart the different wavelengths of light. So that's why they are incorrect. In this one, we're asking to deal with a continuous spectrum. This is more my cup of tea. We have various different wavelengths of light have been absorbed. What does that absorbing is the atmosphere around the sun for that as it's passing out. Here we're asked to state the wavelength of blue-green for hydrogen. And looking at that, hydrogen spectrum 486, blue-green. Will be my answer there. Next one, calculate the frequency. E equals HF is what we're going to deal with there. So we could use E equals HF, but we don't actually have that frequency. We don't have any energy. So not that one, let's rethink it. Below it, speed, velocity, frequency, wavelength, V equals F lambda. Then F is going to be V over lambda. And then that's going to be 3 times 10 to the power of 8 over, remember, and convert this into meters, times 10 to the minus 9. That gives us 6.17 times 10 to the 14 hertz as our answer there. In this next question, we're asked to figure out the energy involved this time. So this will be E equals HF, and it's going to be the 6.63 times 10 to the minus 34 that we've used before. And then we've got our frequency from the previous part, times 10 to the 14. Ping that in, 4.09 times 10 to the minus 19 joules. Straightforward one with that. We're asked to identify the electron transition that produces this dark line. Well, that's got to have been the energy absorbed. And because we're talking here, and these ones we're talking about promotions, where they're moving up the way, so energy is absorbed and an electron's moving up the way, it's going to have to be from electron level, energy level 1 up. So it can only be 2, 3, or 4. Well, if that's the energy that's absorbed, that's going to be the energy gap that has caused that promotion. And because I know we're starting at E1, I can then put the E1 add on that energy that corresponds to the gap, 4.09 times 10 to the minus 19. That gives me minus 1.36 times 10 to the minus 19. That matches up to level 3. So it's got to be a transition from energy level 1 to energy level 3. And it has to be that way around because it's promoted. Energy is coming in and the electrons are going to a higher energy state. And that's what we're doing in that one. In this next one, we are asked to work out the recessional velocity. Let's use the relationship sheet. Okay, so there are 2 with the recessional in it. Now, the fact that we're asked about velocity means I'm leaning towards this one. So if we want to do that, then V will equal Z times C, so times the speed of light. Do we know Z? No, but we do know 3 times 10 to the power of 8. So does that mean we need to use both of them then here? So do we have 2 wavelengths involved? Yes, we do. So we have our observed value and we have the wavelength at rest. Make sure we put them in the correct order. So it'll be the 672, take away the 656, all over 656. Popping that in gives me an answer of 0.02439, and I can just fire that over to the other side, and then calculator takes care of it. 7.32 times 10 to the power of 6 meters per second. So with that one, if like me, you're not 100% sure which way to go, at times you can just look at, so as long as you narrow it down to the 2 possible ones, there's certain situations, one's more suitable, or if you try and do one and then you get stuck, then look and see, can you find out that value another way? And then ping it in, and that should get us our answer there. In this one here, we have a second galaxy with a different spectrum. It has a lower recessional velocity, because that was 7 point, and that's only 4.8 something. So if it's a slower velocity, there'll be less of a shifting, and it shifts towards the red, so to the higher wave, longer wavelengths. So that means it will be further to the right than the sun, but not as far as the distant galaxy. So it's shifted a bit, but not quite as much. I don't know if we're supposed to look and see, well, that's like less, or it's more than, so half of that would be what, 3.6-ish, and this is bigger than that. So I don't know if we need to be specific, like exactly where it goes, but for the moment I'm just going to put it somewhere in between the two lines that are already there. And then talking about the expansion, the reason for this is the dark energy is providing the energy, and that's why it's accelerating the rate of expansion. Another wee fact. In this question, we have an AC circuit, and we are asked to work out the resistance of resistor R, and they two are in series with each other, and the switch is open. Okay, so I don't think we care about the 1.8 then. What does that mean? We have to then look for the resistance. Well, we know the current, we know the voltage, so V equals IR, V equals R equals V over I, so it's going to be 6 is our voltage, and it's 2 milliamps, so 2 times 10 to the minus 3 amps. That gives us a resistance of 3000 ohms, which sounds like the end. However, it's 4 marks. That's not going to be worth 4 marks. What have we done wrong? We have to remember that that is the total resistance. And because R1 and R2 are in series, we just add that together. So 3000 is the combination of both. So the one we care about is going to be them taken away, and that gives you 1200 amps, 1200 ohms as the answer there. Then in this one, we are shown an oscilloscope, and we are told the time base and asked for the frequency. So T equals 1 over F, or F equals 1 over T. Sounds like a good starting point. We can then work out what the period is, which is the time it takes for one wave. And we do that by the time base times the divisions for one wave. So find 2 points, start and end. Start of one and the end of the other. Here it's 4 boxes, which would be 4 times 5. So that would be 20 milliseconds. And then milliseconds is times 10 to the minus 3. So 20 times 10 to the minus 3 meters. And that is what we were asked to show that the frequency is that. For part C, we are asked now to take into account the fact that we're going to switch. We're going to close switch S. So now we've got all the resistors in the circuit. And this is adding a bit of parallel to the circuit. And in parallel circuits, the resistance is lowered for that. So then we need to start puzzling through how that's going to affect it. And we're asked about the amplitude. So the first thing is, we've got the parallel section. That's going to reduce the total resistance. And that then means you've got an increased current. And then if you increase the current, because V equals IR, the voltage would increase. And that must mean then if there's a higher voltage, you're going to have an increased amplitude. In this next question, we are asked to sketch a graph showing current against time for this capacitor charging. Well, we know the time is 6.2 seconds. We've not got a current, but we could work out the current. So the switch is closed. So it's got the 56 kilo ohm resistor, 6 volts supply. So V equals IR, I equals V over R. And then that will be 6 over 56 times 10 to the power of 3, which will be 1.07 times 10 to the minus 4 amps. And that's then going to be your peak value. And then so when the capacitor is charging, the voltage will be increasing, and then the charging current will be decreasing. So we want a curve going down the way, and it starts at the maximum current, which we just worked out as the 1.07 times 10 to the minus 4. And then down, it takes 6.2, so we need an end point at 6.2. And then we want to get some sort of curve thing down the way to go between them. So a smooth line, yes, we'll call that a smooth line for that one. In this next question, they are trying to determine the capacitance of a different capacitor. It's uncharged, it's beginning to charge, and they're asking whether we should increase or decrease the resistance of the variable resistor to maintain a constant charging current across, or in a constant charging current for the capacitor. Well, the voltage is going to increase across the capacitor. So the voltage is building up, like I said, for the previous one. So if that voltage goes up, the voltage across the variable resistor has to go down. With a lower voltage, we'd want to have a lower resistance as well to keep those things going together. I find values help me get my head around these kind of things. So if you have your original voltage and resistance, and we get a current of 2, if the voltage is going down, because more of the voltage is going across the capacitor, if you left the resistance as, in this case, 5 I've put, your current is going to go down. The only way that it's going to solve that problem is if that also decreases by the same proportion. Were to change that to 2.5, if that resistance goes down, then that would then also get the same current flowing through them for that. And that's, yeah, they have to go down in lockstep, to make that work. And then the next one's asking us about the charge. Charge is Q. We have the current, we have the time. That's looking like QIT. And then watch out for the fact that it's microamps, so times 10 to the power of -6. And it's just 28 seconds, so that's fine. Pop that in, gives you 4.2 times 10 to the power of -4 coulombs of charge can be stored, or is stored when fully charged. Then next we're asked for the capacitance. That looks like the value. That feels like C equals Q over V, because we just worked out the charge. So I'm going to bring that with us, 4.2 times 10 to the -4. And then the voltage was 9 is the voltage. Plug that in. Calculator says 4.67 times 10 to the -5 farads for that one. This question is the second of the using your knowledge of physics questions and talking about band theory and solid materials. So here I'm going to talk about any strengths and any weaknesses of the two. Electrons follow. Electrons will fill lower energy levels first before the any upper floor levels. That's a positive thing that it talks about for that one. And this would correspond to the filled valence band and conduction bands, the empty parts of it for there. If the band is completely filled, it will not be able to conduct because there's no energy states available for them to move into. And that's what's been shown here by the fact that says they can't change them while they're working for that. Easier bit I found was the weaknesses of it. Well, it's the size of the band gap that determines whether the material is a conductor, an insulator, or a semiconductor. For insulators, they have a large band gap, and that means that the electrons cannot easily move between the valence and the conduction bands. And that's what I've tried to show here with my little diagram showing the valence and conduction bands. The analogy is saying that the conduction band's only available when the valence band is filled. It's available when there's enough energy in the electron, when the electrons gain enough energy to get promoted between the two of them for that. In conductors, there is an overlap between the valence and the conduction bands. And that's why it is easy for their electrons to move between the two of them. And that's why they do conduct electricity. And then talking about semiconductors, there is a band gap, but it's fairly small. And then that means there is the potential for the electrons to move between the two of them. And the next bit I've talked about is the fact that if you add impurities to the semiconductors, then they will be more conductive. And then if you can remember the difference between the N-type and the P-type, where you're adding extra electrons for N-type. So with a certain type of impurity like arsenic, they will allow it to then conduct more, versus the P-type, where it's something that's electron deficient. So only 3 electrons means that there's positive holes, and then that then allows for the movement again of the electrons. As with the previous one, 3 marks for good, 2 marks for reasonable, 1 mark for limited, and that would hopefully pick up all the marks there, and there might be other stuff you could talk about as well. Okay, in the first part of the last question, we're asked to draw a graph of F against E, so the force against the extension. Now, I treated this like I've treated every single graph I've ever come across in my life, where the one that's on the left is your independent variable that you're changing, and then you put your result on the y-axis. Plot, 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 great. Now, I might be misreading this or not, basically not getting what it's talking about, but it's F first. To me, I wrote it go along the bottom first, but what we're supposed to do is do F going up and down the way and extension going across the way. So I had plotted it with F on the bottom, figured out when I was checking, oh, it doesn't quite work, right, fine, right, do it the other way around. What I didn't read, as I've now read here, is you have not to be penalised if you plot E against F, which is what I ended up doing. But I've now got it in the same format that they were looking for here. I'm not sure how easily this is going to come across. I was finding my eyes were getting twisted trying to look at these. So what I've done here is I've tracked each of the values as they've gone along. So I can see exactly where I am plotting all of my points. I've got up and down the way, every little box is 0.1. So as an example, this point here would be 3.9, would be 10.8. Going across the way, every 2 boxes was 0.1 as we make our way across the way. And then I've then plotted my line of best fit to try and get them as close as I possibly can to all of my points, and tried as best I can not to go beyond the range of the values that we have got. The next part was then to find the gradient of it. So just while I was on this graph, because it was, again, my eyes were, it was not fun, the 2 points I'm picking. So I've tried to get ones that sit relatively nicely on a cross point, because in theory that would make my life easier for putting the numbers forward. So that's what those 2 points are, the points for the gradient, which we'll do now. And then again, because I'm slightly out of practice with the whole gradient situation, I've just marked them in as x1 and y1 and x2 and y2. So m equals y2 over y2 minus y1 over x2 minus x1. I've got my values there, plugged them in, and then that spat out an answer of 3300 as my gradient. And it's to be the gradient of your results for your line of best fit. So if you do have a point in the table that is on your line, then yes, use that. But if your points don't sit exactly on your line, you have to use points that are on your line. So for example, this one up there, you wouldn't be using the point at 2.1. So 7.8, 2.1 isn't on my line of best fit. So make sure you're taking it off of your line of best fit. Okay, so after the palaver of that lovely graph, I was like, oh great, look, there's a wee relationship. This is going to be fun, rearranging, wonderful. We want to work out the modulus, which is E. Great, let's start doing some shuffling then. So if F equals EA over LE, starting to rearrange it. And the first thing I want to do is get rid of the E from the other side. So I'm going to move that over and divide by it. So F over E. And then at this point, I got myself a bit muddled up and confused. I was trying to find out, well, do we have an E? No. Do we have an F? No. But we did, and that was the whole purpose of the previous question. Oh, I'm just realising they tell us using the gradient of your line of best fit. I was trying to work out how the heck I'm supposed to know to do this. Well, I eventually got to the fact that the gradient we did F over E, which matches up with what's in the relationship. So the left-hand side is now just our value of M. So now I'm going to keep rearranging. The L is going to come across and multiply by it. The A is going to go across and divide by it. And then I can put my numbers in. We got 3300 for the gradient. L is the original length, 1.5. And A is the cross-sectional area, 5.9 times 10 to the power of minus 8. And then plugging that in gives me an answer of 8.39 times 10 to the power of 10 pascals. You might have had slightly different depending on your results, because it was your line of best fit that you're to use in that one. And if you read the question, if only someone had told me that all the time to read the question carefully, I could have made that more straightforward. And the last one is saying there is systemic uncertainty associated with the data. That means that something's impacting all of your results. So it's all skewed away from the origin. That's the proof that it does not go through the origin. There is something affecting the results and shoving it away from the origin. That brings us to the end of the question and the end of the paper. That's how I attempted each of those questions. Thanks for watching. Goodbye.